Alright, new chapter 10, which is the application of differentiation. We'll do 2a, which is tangent and normals, and 2b is the rate of change. Tangent and normals, so that shouldn't be anything new. Would be when you have an equation of a straight line, you need to determine the equation. You will need the gradient. You will need the coordinates of a given point on that straight line. What's going to be applicable from the derivative of a function that is defined by f prime of x is that new function for that value of x will measure the gradient of the tangent at each point along the curve. So the gradient of the tangent at the point x1, y1 of that curve is given by the derivative f prime at that given point. Then we get an expression of the function of the straight line, and we define the gradient of the tangent with notation is mt suffix as a derivative of x equals x1. An example, so you can go through that example. It's about you have your function, you differentiate, you substitute the coordinates of that point, you do a little bit of algebraic manipulation up to simplify the rule to make y the subject, and you get the equation of the tangent, and the gradient value is -1. Different example, you will have a polynomial function. So the application here is to differentiate polynomials. You can use your CAS calculator. So on the calc page, under menu calculus tangent line, you can get the actual value. So you define your rule as an expression in terms of the variable x, comma, then you define the actual value that x is taking, and you will get the expression of that straight line. Another particular straight line is what we call the normal. The normal is a line that is perpendicular or right angle to the tangent. We annotate the gradient of the normal mn. To determine its value, you need knowing that you get the tangent equation is two lines that are perpendicular. The product of the gradient is equal to -1. Okay, by transposing and make mn the subject, we can determine its value, and then to determine the equation of that straight line, we just apply the equation by substituting x1, y1 and the gradient. So here's an example. You have a function f. It cuts the y-axis. So here there's a little bit of a trick. You need it doesn't give you the coordinates of the point at which you determine the equation of that straight line, so you might have to do a little bit of understanding from that text, and I'll get back to that. First, I just want to go to the actual question. You need to find the equation of the normal, so it's an equation of a straight line. You will need to determine the gradient of the normal. Now we go back to the first sentence. To find the actual point at which you want to determine the tangent and the normal, it's when you cut the y-axis, which means it's the definition of your y-intercept. You define x equals 0. So you differentiate, you find the gradient of the tangent, which is 3. Okay, and we can determine the equation of the tangent, which is y equals 3x minus 1. Okay, now also notice the y coordinate of the or the y-intercept is going to be -1. That's how you determine you have your x1, y1 here. Okay. Now, as we know the gradient of the tangent, we can move on to the second part. The gradient of the normal is -1/3. We substitute the same x1, y1, and we get that equation. Just to confirm, the product of those two gradients has to be equal to -1. If you do a visual representation, so f is a quadratic, so that's the blue curve. You can see it intercepts the y-axis at y equals -1, which is what we calculated. It's in red you have that tangent, so it's just sliding along that blue curve at that point, and then you have the normal, which is right angle at that point to the tangent in red. 10b, rate of change. So the first part is nothing new. So the average rate of change between 2 points, x equals a, x equals b, is given by that expression. Okay. Now, as we were using the first principles, we were doing something with the limit using that rate of change. As it gets, those 2 points gets closer, we move on to the next statement, which is the definition of the derivative. So the instantaneous rate of change of f of x at that point x equals a is given by the derivative of f when x equals a. Couple of examples. So with the first one, so it's exercise 10b, it's question 1. For the function, you have a function given like that, so it's a quadratic. To determine, you have to determine the average rate of change between 2 fixed points, variable points, one of them, and then C, you need to determine the instantaneous rate of change. Okay. So with part A, we just substitute x equals 2, x equals 3, we get that value. Okay. With part B, the first point is x equals 2, the second point is x equals 2 plus h. So your expression will eventually in terms of h. So you substitute that, make sure you do your order of operations correctly, you expand the brackets, regroup the like terms. In the fraction simplifies nicely and you get 3h plus 18. Alright, with part C, you could have used part B kind of by using the first principle, but here we just differentiate, so that's f prime of x. We substitute x equals 2 and you get 18. That confirms part B if you were to use the limit. Before we move on to the last example, it's about, we still using the rate of change, it's a little bit about a physics language or application. So you will look into this exercise, questions that can be related to the motion of an object in a straight line. So a car moving along in a straight line, an elevator moving upwards, downwards. Okay, a little bit of a definition first. Point O will be your origin. So for the elevator, it's your ground floor. It will considered as a particle, so it's single point, and will be moving in a straight line. Moving on that straight line will be a directional one, so it can be positive or negative. Then the definition of its position or displacement is x meter from the origin. Again, it's directional, so it can be positive or negative, so just keep that in mind. It's not an actual, it's a difference from the distance. Next one is the velocity. The equivalent in absolute value, it's the speed, so it's in meters per second, and the acceleration is, we define as a, and it's in meters per second squared or meters per second per second. Below you have your notation. So velocity is the derivative of the displacement in terms of t. the acceleration will be the derivative of the previous one, which is v in terms of t. So with the application, the typical questions, again, is nothing that shouldn't be really new. It's about differentiating. You have a function. Now the function is x as a displacement. It's an expression in terms of t. T is your time variable, which is defined here in seconds. Just pay attention to the units as well. X is in centimeters. Find the velocity v as a function of t, so that is just differentiating. So you differentiate, you can do it by hand or using the polynomial rule or just on a CAS calculator. B, at what time and in what position will the particle have zero velocity? So that expression that you have, you turn it into equation, you make it equal 0. It's a quadratic equation, you factorize it whichever way. Here look for a using a cross product. Okay, if that method doesn't work, use the quadratic formula. There's also completing the square. That's more to find the turning point. So here we have two values, t equals 1, t equals 2. We substitute those respective values to find the actual displacement, the position. So we need to with those values go back to the original expression of x and find the actual values in by the way, that's not in meters, that should be in centimeters as given into the question. And I just realized I might be a little bit in the way. So here that's t equals 2 on the left and t equals 1. Okay, alright. Part C, find its acceleration. So you differentiate again, this time the previous expression that you find in question A. You had a quadratic for v, so A will be a linear expression in terms of t. That's 12t minus 18. Find its velocity when its acceleration is 0. So you solve the equation A. Sorry, we still at C. So find its acceleration at those instants. So it's for t equals 2 and t equals 1. You substitute that, you get, again, it should be in centimeters per second squared. And notice here it's a negative value, which is fine. Again, it's directional. It could have a positive or negative direction. Alright, part D, your acceleration is a linear rule. We solve that, we make it equal 0. That's a linear equation. T equals 3/2 or 1.5 second. You substitute into here. That gives you a again, just be careful, it's asking you for the velocity, so you need to use your velocity expression. Substitute t equals 3/2 and it will get a negative velocity of negative 3/2, again centimeters per second. And that's the end of today's session. See you next time.